Okay, good afternoon and welcome back. Yesterday we arrived to these slides where we described the whole verifiable credential. If you remember the three main components of a verifiable credential, you have the metadata, the credential subject that contains the claims made by the issuer on the subjects, and then the proof. In this slide, you can see immediately that the metadata are on the top from context to valid until. We can consider metadata also the credential status, that is the properties used to deal with the revocation or suspension of the verifiable credential, the credential subjects that contain for sure, the DID of the subject, in this case, subject and holder match, and all the other properties that are typical of, let's say, the type of verifiable credential that the issuer is issuing. The proof essentially today require type property that is data integrity proof. The crypto suite, the name of the crypto suite, use the algorithms used to generate keys and sign, of course, the algorithms that the verifier need to use to verify the proof. The property created, a timestamp when these signatures been made by the issuer, the verification method that provide the whole DID of the issuer, also with the fragment if the DID document of the issuer have more than one verification method. Proof purpose, super important because we always have to specify the purpose of a signature and what are the meaning of that signature, and then the proof value. This is the most simple way to deal with the proof property. So a single signature made by the issuer for integrity and authenticity of the verifiable credential. But the specification also give us freedom to made something different than a simple single signature. For example, the specification allow us to define a proof set. That is a set of independent proof. This set can be useful, for example, when the document, the information, in our case, the verifiable credential, must be or need to be signed by multiple subjects, multiple issuer or multiple entity. With proof set, the order of proof does not matter. What does it mean? The property proof is essentially a vector of proof. You can see there the first one, proof, made by issuer 1, and a second proof made by issuer number 2. Okay? So if there are applications that require 2 or more signature, the specification give us the right to do that using the proof set property. Just to push a bit on this, the order doesn't matter. So if issuer 2 sign after or before issuer 1, it doesn't matter. We simply put both signature on the credential. We can do something more. We can also have a proof chain that is differently from independent proof set, a chain of proof. Again, useful when the same information need to be signed by multiple entities. But in this case, the order is important. And the order, let's say we can use proof chain when the proof occur matters. So when it is important, also the order of the signature. It requires at least one proof with an identifier, and the following proofs use the previous proof property to reference the previous one. In this case, we use a URN as an ID in the first proof, and in the second one, we simply refer to the previous one. Of course, in case of independent signature with proof set to validate the information, the credential, we need both the signature must be valid, with proof chain also, but typically for example, the second proof also protect for integrity also the previous one. Okay? So essentially, these signature also cover the previous proof. In the sense that you consider also the signature before, when you calculate the hash and then the signature on the information. So, proofs use digital signature for authenticity and integrity of verifiable credential, and this proof enable integrity protection, so to make the verifiable credential tamper evident, make statement that can be shared without loss of trust when we share and presents our verifiable credential, authentication as a subject with a particular DID, and delegate authorization for action, for example, in remote execution environment. The information of DID is very important within the verifiable credential. And if you remember, the whole framework is exactly inside the dirt layer where we present verifiable credential, that we exchange also the DID of the holder, because is within the credential subject of the verifiable credential. So this is very important, because sometimes the figure on the word framework is misleading, in the sense that you can expect that you directly exchange the DID. You don't exchange directly the DID, but you exchange the dirt layer a verifiable presentation that contains a verifiable credential that contains a verified DID within the credential subject, verified by who? By the issuer. Okay? So, just to recap, the properties within the proof properties, properties, ID, that is an optional identifier for the proof, type, data integrity proof purpose, the classical that we already know from the DID document. So assertion method, authentication, and key agreement essentially prevent the proof from be applied to a purpose that is not the one intended by who made the proof. The verification method, we use again this name for the property to provide the information on the DID, so essentially to the public key of the issuer or of the holder, and the crypto suite. This is the identifier of the crypto algorithm used to generate keys and, of course, to prove, to sign and verify signature. Created, the time, date and time the proof was created. Expire, in the example, we didn't use the properties expire, but that's super important also if you want to set a limit in the validity of the proof. Challenge is very important and sometimes is used in conjunction with nonce. We will see step by step all the all the verification steps again made by a verifier of a verifiable credential, but also all the steps when an issuer issues your verifiable credential. And what is important, in particular, when you present your verifiable credential, is that when you first contact the verifier gives you back a challenge, a nonce, that you consider to made a fresh proof for avoiding replay attacks. The challenge is provided by the verifier. Nonce sometimes is used directly also from directly from the other. One of the reasons can be also for privacy, because if possible, I want to avoid to be linked, for example, in the value of the signature. Proof value is the proof itself, and previous proof is used with proof chain. So let's see now what is the trust model behind these three-party models based on the use of verifiable credential and verifiable presentation. Issuer prepare the verifiable credential and sign it. So made a credential verifiable. Verifiable credential, first of all, what does it mean, trust model? It means that every actor that interact within the framework consider this model through. And so all the implementation and actions happens knowing very well this trust model. So issuer issue verifiable credential and sign it. Verifiable credentials are transmitted in a way that clearly establish that the issuer generated the credential and that the credential was not tampered with in transit nor in storage. So an holder trusts an issuer and trusts the verifiable credential that receive, of course, verify every single property of the verifiable credential, but this is the trust model behind the framework. All entities in the ecosystem expect the VDR to be tamper evident. That means that a VDR can also not provide immutability. So at least I have to be informed or have evidence that something has been tampered on the VDR. Holder and verifier expect the issuer to stand by claims it makes in the VC about the subject. So we trust that the issuer has verified before accepting some claims about the subject, and they expect that the issuer behave correctly, and so he revoke immediately when needed a verifiable credential, such that both the holder and in particular the verifier can check the status of the credential during the authentication process. And then we arrive to the open point. The holder may trust the issuer claim because the holder has a pre-existing trust relationship with the issuer. This is related to the last point, how verifier decide which issuer to trust, essentially. So, and this is really an open point. There are a lot of different possible solutions. Well-known organization, for example, may trust Polytechnic of Torino, may be trusted by many verifiers simply because of their reputation. No? Classical example is a university, the government. Issuer and verifier might be members of a community in which all members trust each other due to the rule of membership. For example, if you become a member of, I don't know, the ETF has some, provides some service through an issuer, and you are part of you are a member of the organization, typically you trust the service they provide within the community itself. Verifier may trust a trust service provider which rank issuer and list them in a trusted list. That's another possible option. I see in real implementation all three. Anyone can prefer one over the others. Other solution can be possible in the near future. So the implicit trust on, let's say, there is no specification at any level of the framework that say, okay, the solution is this one. We are open again to implement the solution that we consider the most appropriate for the application that we are developing and deploying. The point before is that anyway, implicit trust does not imply that the verifier must know anything of the issue. The point is that you simply trust, and this implicit trust from the implementation point of view means that you know very well the DID of the issue. As you know, in security, at a certain point, you must put the trust on something, and then you can move the trust ahead. For the verifiable credential, the core of the trust is the well-known DID of the issuers. It's the root of trust in this case. This means that also a solution for storing in a secure way this well-known DID in the holder is required. Another possible option for trusting an issuer is what typically happen in your real life. When a friend of you typically use a service and you trust your friends, you typically then trust also the service. No? So this happens sometimes. This also can be an option to make your own list of trusted issuer. Extensibility. The data model enable what is called permissionless innovation. That means that you are paying a lot of attention, free to extend the vocabulary, in particular within the credential subject, because you are more or less free to define your properties. This means that you have to extend the machine readable vocabularies, essentially the context, and then you can extend the data model. Another option in terms of extensibility, so another way in which you can extend the data model is given by the fact that the specification support multiple crypto suite. So you can select the crypto suite that you prefer, the one that you consider the most appropriate for your implementation. That can be traditional crypto, a DDSA, a CDSA, it depends. Or if you want, for example, move to post-quantum cryptography. You are all free. If you think that there is a particular algorithms that is suitable for your application, to start discussing with the W3C and define with them a crypto suite. Let's make an example. So in context, I essentially I have to create a JSON context that contains the new terms and publish the JSON context somewhere accessible to the verifier. So I, for example, here define the term new term. Then in the context, I put on, let's say, after the, it's moving by itself. Within the context, I put also the link to the new vocabulary, and then I'm free to use the new term, in this case, within the credential subject. Why it's important? Because me as an issuer, if I want to inform the verifier about the schema of the credential, to give him all the information to, let's say, consider in the proper way the meaning of the different properties and take decision in terms of, sure, authenticity, but also of the credential, but also for authorization purposes. These are examples of existing crypto suite. The one on a DDSA version 1.0. You can go to W3C website and have a read. Essentially, they describe in details the algorithms, how to use them, how to use the algorithm for signing, for verifying. The one on SCDSA, BBS is something quite hot in this period because it's the algorithm for dealing with zero knowledge proof. And quantum safe crypto suite. This is while a DDSA and a CDSA crypto suite are already recommendation, BBS is a candidate, means that they are still working on it. A friend of mine prepared the quantum safe crypto suite, but today is still a community group report. So is far from being a recommendation, will be in the future. The community is working on. In this one, I think this is also a topic of this course. Specify how to use MLDSA. It is one of the 3 NIST selected post-quantum algorithms for signature. Now, some advanced concept for the verifiable credential. Integrity of external resources. Sometimes verifiable credential also contain links to external resource. This you put in credential subjects or in some metadata sometimes, depend, you put a link to an external resource. And so what is important in this case that you deal with the integrity of the external resource. This applies to cases where there is an external resource that is remotely retrieved. The issuer and or the verifier may have locally cached copy of a resource. So it's very important that you put links to external resource. You also have, as an issuer of this verifiable credential, deal with the integrity, because you don't want to assert a certain claim. No? This is the link to that specific resource and not being sure that the resource maintaining its integrity. No one tamper with the external resource. So you can do that. You can use related resource property, for example, to put the hash of the external resource within the verifiable credential. Okay? Super simple. Reflect, yeah, please. It depends who is the actor that is storing the resources. Of course, every time that you receive access requests from entities, you can always link. You can link by yourself, and you can, let's say, make linkability if you collude with others. For sure, I got your point. Every time you as a verifier receive a verifiable credential from the same entity, and you understand this because contain exactly the same information, whatever it is, you can always link. The things change in the sense that if you are the only one in the world with that hash, I link you. If the whole community of user, no, 1,000, 1 million, have a credential with the same value, linkability is, let's say, less strong in the sense that, okay, it's one of the 1 million user. So it's very important also the numbers of users that have this particular data in the credential. Yeah, please.
Integrity. But I remember well yesterday we say that it's part of the operation side. Why?
Because integrity is integrity of the link. But if someone changes directly the resources, you need, in this case, related resource, the hash of the external resource to give the verifier of the credential a way to check that the resource has not, the external resource has not been tampered with. And this implies also that if an issuer are also the service behind maintaining that external resource, you have to implement a way to protect the resource itself. Refreshing also is important. Refreshing of the verifiable credential. So the issuer can also use the property refresh service to inform the holder about where to contact the issuer for refreshing the credential. Refreshing means everything. It means refreshing of the metadata, for some reason refreshing of the credential subject. Sometimes is the refresh of the proof made by the issuer that, for example, can use the property nonce just to generate essentially a new and different signature on your credential. Another property can be term of use. Essentially is the way issuer and holder can explicit the term under which a verifiable credential was issued or a verifiable presentation generated by the holder. The issuer places the term of use in the verifiable credential. The holder, of course, can use this property in the verifiable presentation. The property term of use lets you, as an issuer or as an holder, to express the term of use of the credential. Now, we already said many times, after authentication, that means check the authenticity of the whole verifiable credential, the properties in the credential subjects are used for authorization purposes. So what typically happens that after authentication, the credential subject move forward in the chain of authorization, and the authorization algorithms give you access or reject access to a specific resource. Again, the authorization is out of scope for the verifiable credential specification. They only mention role-based access control or attribute-based access control. Is up to your application to implement the authorization algorithms that you think fit well with your specific application. Okay, now just for a short recap of the whole framework and what we can really understand layer per layer. If we stay at the DID layer and someone provide me his DID with a challenge and response algorithm, I can challenge the other party, the peer, and if the challenge and response is successful, I know that in front of me, my peer is the one that own the private key behind, or not behind, correlated, related to the public keys pointed by the DID. But I know that the peer own the private key. I don't know nothing more. I don't know who is the peer. The use of the verifiable credential and the authentication, the validation of the verifiable credential make me trust something more. I know that the person that own the private key, the DID, is in the verifiable credential. So I expect that the issuer has also verified the ownership of the private key. I trust what is the description of the identity within the credential subject made by the issuer. This is something more that I know. And since I trust the issuer, I know at this point exactly who is the peer. So I need to verify all the information through the wall layer of the framework to arrive to the final decision and trust on the peer that is exchanging or is presenting a verifiable credential to me. Now, verifiable presentation. The verifiable presentation is the data model that holder use to present a verifiable credential to a verifier. And the verifiable presentation is created and signed by the holder. Verifiable presentation can express data from multiple verifiable credentials and can contain also some arbitrary data or contain multiple verifiable credentials. The typical case is a verifiable presentation that contain one single verifiable credential, but you can also present more than one. Maybe because you want to present to a verifier information that are in different verifiable credentials. So if the verifier trusts the issuers of the different verifiable credential, or just one, if is a single issuer that has issued the verifiable credential, can combine the information to complement the data and have a rich information about the identity of the holder. So VP are used to present claims to a verifier. Typically, while the verifiable credentials are long-lived credential, verifiable presentation are short-lived and always bounded to a challenge provided by the verifier. This means that wallet typically store verifiable credential. They don't store verifiable presentation, but generate a verifiable presentation of credential on the fly. So when the subject, the user of the wallet, decide to contact a verifier for authentication purpose. You never store a verifiable presentation. Also because every time you want to be authenticated by a verifier, typically the verifier provides a new challenge to avoid the replay attack. So again, a verifiable presentation is from the implementation point of view, a JSON file. This is the components. Again, metadata. Then the wall verifiable credential, one or more than one, and the proof. When required, the holder with his wallet generate and sign the verifiable presentation and present it to verifier. Let's go through the different components. Again, the context, that is essentially the vocabulary that both peer knows to understand each other. For verifiable credential, today the reference is still the verifiable credential specification version 2.0. Then the type, the first value of this vector is always verifiable presentation. Do you remember? This is also true in verifiable credential. Type, the first value is always verifiable credential. For presentation is always verifiable presentation. Then you, as an holder that knows the system in which you are interacting within, you can specify also the type of the presentation. So this presentation, in this case, is an example. Then, holder. Sometimes the holder also specify who is the holder of the credential. So typically specify itself, putting here is the centralized identifier. For example, when I want to present a self-asserted verifiable credential. So a credential that is not signed by an issuer because it's self-asserted. I issue myself a verifiable credential, for example, because I want to simply prove a verifier one of my choice. And so, since there is no essentially in this way, the holder can say, oh, the holder of the verifiable credential. Then the word verifiable credential, I cannot, let's say, simply copy and paste part of the verifiable credential. Otherwise, the proof is not valid anymore. So I have to put the word verifiable credential and then the proof. It is exactly the same property and that use sub-properties that we have already addressed in the with verifiable credential. There is only one point that change with respect to the proof properties. So there is one value that is for sure different from a proof made for a verifiable credential. Can you spot it? Any idea? Verification method. Because in this case, the DID is the DID of the holder. Because the entity that is signing is creating this proof is the holder. Because we are within the verifiable presentation. On the verifiable credential, verification methods is the DID of the issue. Okay, let's recap the different properties. ID, an optional unique identifier of the verifiable presentation. Type, always verifiable presentation. The first value, the other one, also more than one if you want to specify, are selected by the holder itself. Verifiable credential contain all verifiable credential, one or more. Again, you can have a vector of verifiable credential, but you have to put inside the wall verifiable credential. Holder, a URL or a DID, identifier about the holder that is present in the VC and the data integrity proof. Okay. Let's make some exercise on this part. Please, let's try to make this at least to have an idea. Do the exercise by yourself, and then we can see the solution. So the exercise is asking us to generate a WP, to write a WP, secure with a data integrity proof that wrap and contain a self-asserted verifiable credential. And in doing this exercise, please pay attention to the use of the holder property. So just take a few minutes to sketch your solution, and then we see. Okay, so let's start with the basic component of the verifiable credential. We can take them from here. So we define the context for our verifiable presentation. Type verifiable presentation. They ask us, the exercise asks us to define wrap a self-asserted verifiable credential. For example, I don't know, food preference, presentation. So we will wrap a self-asserted credential on our food preference. Then within the verifiable credential, we put a wall verifiable credential, but since is self-asserted, this means that there is no the proof made by the issuer. So within the verifiable credential, oops, we put a wall credential. Then let us define better. So self-asserted. So no we need the context for sure. Type. There is no reason for the properties ID because ID is the unique ID of the credential from the issuer point of view. So a verifiable credential, we decided to make an example on my food reference credential. Issuer is the DID of the holder. We can also avoid the use of valid from and until, short-lasting self-asserted verifiable credential. In the credential subject, I have the DID of the holder. That, as you can see, coincide with the property holder in the metadata of the verifiable presentation. Then, of course, in the credential subject, I have defined my vocabulary to, or the verifier, the system in which I'm interacting has already verified the vocabulary for defining the properties about my food preference, as an example. And what is needed at the end, so the verifiable credential is self-asserted, so there is no the proof property, but we, as a holder, sign the verifiable presentation. And here, the verification method in the proof is the ID of the holder. We can also, for example, specify that since we use the properties holder in the metadata, we can also avoid the use of the DID in the credential subject or maintain it. Okay, so that's the solution to the exercise. Any question on this? Everything is clear? The only, let's say, things changed by the classical situation is simply that we ask for a self-asserted verifiable credential. For the rest, if you want to wrap a verifiable credential provided by a real issuer, you simply, again, copy the whole verifiable credential within the verifiable presentation and so on. You will have also the proof made by the issuer. Now, let's move to the last two topic for today. Some framework. So from the general point of view, if you remember for what we said yesterday, self-sovereign is an identity solution that works at application layer. So every time you as an holder interact with an issuer, and also when you interact with a verifier, you first of all open a secure channel with the last version of TLS to protect the communication between the two peers. On top of that, you can exchange verifiable credential and verifiable presentation. Sometimes you exchange JSON files directly. In other cases, you present credentials or verifiable credential and verifiable presentation in JSON Web Token format. So as you include VC using JSON object, signing and encryption, OSE, representation. The classical JWT that I think you have already seen in other courses. In this case, the presentation contains within the verifiable credential field directly the JWT. You have to specify in front the media type, data application, verifiable credential in JWT format. And also you specify the type enveloped verifiable credential. You can also envelope the verifiable presentation and use the JWT as in the previous example. For example, the IOTA identity framework use JWT format for verifiable credential and presentation. And that's it for today. You have one more slot with Professor Azzeni on exercises. Next time, we will restart from the analysis of the security and privacy consideration that the authors of the verifiable credential standards as defined. As for the ID recommendation, also the VC recommendation, in particular the last one, that is the version 2.0, specify some and define some consideration that you have to take care when implementing verifiable credential.